Hey, hello everyone. Welcome to the virtual SI session. Um, if you can hear me, can you type out yes in the chat just so I know that I'm being heard? Okay, awesome. So today we're going to talk about single source shortest path algorithms and uh, the main what single source shortest path means we're talking about graphs that have weights, the edges are weights, and we want to find the shortest path to go from a source vertex all the way to probably maybe every other node that's reachable from the start vertex or to a particular target destination. So we're going to talk about two different kinds of algorithms that we can use to achieve this. We're going to start off with Dijkstra's algorithm. Then we'll talk about some of the issues that arise with Dijkstra's algorithm and what is the other algorithm that is the directed acyclic graph DAG algorithm that overcomes some of the pitfalls with Dijkstra's algorithm. So Shivanku will be talking about Dijkstra's algorithm and we'll be using some visualizations so it's easier to explain the whole algorithm. And from then on, we'll talk about the single source shortest path. So Shivanku, do you want to start with Dijkstra's algorithm?
Yeah, sure. So Raj, one of the questions that comes to my mind is that if we already had Prim's algorithm, then why do you think we needed Dijkstra's algorithm? So any input on that?
Um, so Prim's algorithm is to find the minimum cost spanning tree. Um, with that, we are actually trying to find minimum cost spanning tree would mean every particular node should be included in the graph. And so shortest path is a different concept. The shortest path, you're actually just trying to find, we have a source and we have a destination and we're trying to find the shortest path from the source. So does not include, we do not care about every particular node in the graph. So that's, I think, one of the key differences between Dijkstra's and Prim's algorithm.
Yeah, that's correct. And also another key point is that when we are dealing with Prim's and Kruskal's algorithm, we are dealing with graphs which are undirected. So the main key difference is that Dijkstra's and Bellman 4 and all these algorithms, they are specifically meant for graphs which are directed. So even though they can also be applied on undirected graphs, but the same cannot be said about Prims and Kruskal's. So Prims and Kruskal's can only be applied on undirected graphs. So that's like one of the key difference whenever you are doing a question in an exam and that gives you a graph and then you're thinking, okay, which algorithm do I need to do? Then you need to keep in mind, are the weights negative? Is it just directed graph? Does it have cycles? So you need to answer all these questions and then take an approach to which algorithm you should probably be using to solve that question. Okay, so let's start with Dijkstra's algorithm. So it's pretty much, I would say, similar to Prim's algorithm. So for someone who is familiar with Prim's algorithm, it should be really easy. So all we try to do is we are given a source. We go from source node and we try to reach all the nodes, and in doing so in minimum cost possible. Okay, when I say minimum cost, what we are trying to do is, let's say we have a node A and we have a node B, and we want to reach a node C. So we try to traverse the path with which our cost will be minimum. So there might be a case when we can reach A to C directly, but it is costly. Whereas if we go from A to C via B, it's a little cheaper. So we'll take the cheaper option. But if I am a computer, I don't know what A can lead me to, right? I, being a human, can know, okay, to reach C, there are two paths. I can go either from A to C, or I can go from A to B and then to C. But when we are talking in terms of computers, what we need to do is we go on each and every node and we only know about our neighbors. So let's say if I am at A and A has outward arrows to B, then all I know is that the next node from me is B. and it's at 2 or 3 or whatever cost away from me. That's all I know. And as I keep on progressing down the graph, I keep on discovering more nodes. Then I keep on knowing, okay, there was another path from A to C, which was probably better or probably worse. So that is how we apply all these algorithms. Whenever you're thinking of these algorithms or solutions, you should think from a computer's perspective that we know this, but it's not so obvious for a computer. And a computer only knows about the current node and the nodes which are in its neighbors. So I'll show you a quick I'll do a screen share and I'll show you guys a visualization which will make it even more clear what I'm trying to say. So I'm just checking if my screen is sharing on a laptop. Yeah. So what I'll do is let's assume this to be the graph that we are using. Okay, and so in this graph, as you can see, we have nodes from 0 to 7, and we have a cost, and it's a directed graph. Okay, so what we do is we need to specify a starting vertex. Okay, because like in Prim's algorithm, we have a starting vertex, right? Whereas in Kruskal's algorithm, we wrote each and every edge in terms of non-decreasing order, and we started, right? So that's also a main difference between Prim's and Kruskal's, and Prim's Discastras and Kruskal, that in Prim's and Discastras we can give a starting node, uh, whereas in Kruskal we cannot give a starting node, right? So let's give 0 as our starting node. So what happens when we do that is the cost for each and every node besides 0 is infinity. And the cost of going from 0 to 0 is infinity, because it's obvious. If I am at 0, I want to go at 0, the cost would be 0, right? But I don't know about cost of going from 0 to any other node right now. So I set it to infinity. Okay. So when I'm at 0, I discover 3, which is like 6 cost away from me. Okay, what else do I discover? I discover 1, which is again 6 cost away from me, and I discover 4, which is like 4 cost away from me, right? So these are the only 3 outward arrows from 0. So I'll go in the table and I'll update 1's cost to 6, 3's cost to 6, and 4's cost to 4. Okay, then what I do is I check back in the cost array and I select the minimum occurring cost. Okay, so the minimum occurring cost after 0 was 4, right? So I go at node 4. Okay, and then I'll check what are the other outgoing arrows from 4. So one outgoing arrow from 4 is towards 6, and it gives me a 9 cost, right? So I'll update the cost for 6 in this table as 9. And I'll add 4 because I am going from 0 to 4, which is costing me 4, and then I'm going from 4 to 6, which is costing me 9. So the total would be 13, right? So I'll again check the array and check for the minimum cost. The minimum cost, I'll go a step back. The minimum cost right now is 6, 6, 13. 4 and 0 we have already traversed, so we'll go towards the first 6, right? So we'll go to 1. Then we go to 1. And on going to 1, do we discover any other node? We discover that there's a cycle between 0 to 1, right? And whenever we have a situation in which we are discovering a node which we have already discovered, we break out of that cycle. Okay, since that node is already known and we don't want to be stuck in the cycle, so we break out. Okay, we go again back to our array to find the next minimum node, which was 3, right? It has a cost of 6, so we go to 3. We check, does 3 have any outgoing arrows? It does. It is giving an outgoing arrow towards 1 and towards 7, right? So what we do is, since this is again a cycle, 1 is already discovered, I don't do anything, I break out. And since 3 is letting me go to node 7 at the cost of 8, I'll update it to 8 plus 6 equal to 14, because if I need to go to 7, I'll go from 0 to 3, which is costing me 6, and then 3 to 7, which is costing me 8. So the total is 14. Okay, then I again go back And so now we are left with node 2, node 5, node 6, and node 7, right? So I select 13, okay, which is the cost for node 6, which is the minimum, right? Now I check node 6. Are there any other outgoing arrows? There is. So we can go from node 6 to node 2 by a cost of 5, right? So we'll update the cost for node 2 as 13, which is the cost to reach node 6, plus 5 more to reach node 2, right? So as you can see, we have updated the cost to reach node 2 from node 6 as 18. Okay, and we have also mentioned it in the path that in order to reach 2, we'll take node 6 at the path as the path, right? And now we again check what is the minimum value. So the minimum cost is 14, which is at node 7, right? So we go at node 7 and we check what are the outgoing arrows. Okay, so the outgoing arrows from 7 is 1 going towards 6 at 6 cost, but we have already discovered 6, right? So since 6 is already known and this is a cycle, we'll break out of this loop. Again, we go back and we check what is the next value, which is the minimum. We have a competition between 18 and infinity, and it's obvious that 18 is the minimum cost. So we go to 2, which is an occurring as 18 cost when we go to 2 through 6, right? So we go to 2 and we check, is there any other outgoing arrow? So we have 2 outgoing arrows. One is going towards node 1 and one is going towards node 4. So the one going to node 1 is giving us a cost of 1. So we are already at a cost of 18. If I add that one, I would be going to 1 at a cost of 19. That's not required. I have already discovered 1, right? So I'll break out of that. Now it has an arrow going from 2 to 4, right? We have already discovered 4 through path 0. So it's not required either. So I break out of the loop, right? And so there's just one node which is left now, 5. So when I go to 5, there are 3 outgoing arrows. I can go to 1, I can go to 6, I can go to 7, right? At the cost of 4, 6, and 7 respectively. So I go to each one of these and realize that I'm done with all the other nodes, right? And that's how Dijkastra primarily functions. So as you can see, we tell what path every node has to take in order to go through this, which I'll show with my animation. So as you can see, in order to go to 0, we had to take path 0, right? Because we have to stay at 0. In order to go to 1, we had to go from 0 to 1. In order to go to 2, we had to take from 0 to 4 to 6 to 2. Okay. In order to go to 4, we had to again, so in order to go to 3, we had to go from 0 to 3, right? And in order to go to 4, we had to go from 0 to 4, right? For 5, we don't have a path because if we go to 5, it will lead us to a cycle, right? So, and as I told you, whenever we are going to a path which will lead us to cycle, we break out of the path, okay? And we'll go to 6 through 0, 4, and 6, okay? And as you can see, 0, 4, and 6. And we'll go to 7 through 0, 3, and 7. Okay. So this is our final answer. This is the Dijkstra's shortest path in order to traverse all the algorithm, all the nodes given in such a way that even if we have cycles in the graph, then we are able to tackle those cycles and find out the shortest given path. But this brings me to a thought that what would happen if we had like negative weights. These arrows had negative weights. What if this 6 was minus 6? What if this 1 was minus 1? What if this 2 was minus 2 and we were in a cycle? Would we keep on decreasing the cost we take from 0 to 1 by minus 2 every time? So what do you think about this?
So that's a good question. I think Dijkstra's algorithm has the one pitfall there and would fail in that situation. because it does not work with negative weights. So it works really well for positive weights, and it does this whole algorithm in a time complexity of V E plus V log V, because we got to go through every edge at least once. So E and then plus V log V. So it's a really good algorithm. It works perfectly well for weights that are positive, and it's powerful, but it's limited in that sense. So and then we there's another algorithm. If you want to find the shortest single source shortest path for an algorithm which has for a graph that has negative weights, you definitely need another algorithm. And one of the other algorithms that's there is Bellman-Ford. And Bellman-Ford is a good algorithm because it's very robust. It works with every different kind of graph, no matter what, that it can detect negative weighted cycles. It can work with negative edge weights. It can work with positive edge weights. But it is kind of slow. It works in O of VE, so that is slow. Now we can overcome both of these algorithms, and in another algorithm called the single source shortest path for directed acyclic graphs. Now this algorithm is a linear time algorithm, and so it does have some prerequisites that it can allow for negative and positive edge weights, but it should not have cycles, and it should be a directed graph. And we'll talk more about the cycles portion as we go through the algorithm, because it is limited, but you can push this algorithm a little beyond its boundaries to make it work and it might work for some particular instances or situations where the graph has cycles, but not for every. And we'll talk about what situations that if a cycle is present, it would work. So let me first show you what the main idea is. And so here, as you can see, the main idea for the single source shortest path for a DAG is, and we can see here that Bellman-Ford does it in O of VE time. And we can do better with no negative weights in O of E plus V log V using Dijkstra's, which Shivanku just talked about. Well, we can do even better with directed acyclic graphs. We can calculate the single shortest path using O of V plus E. And so the main idea behind that algorithm is this. We initialize the distance to every vertex as infinite, and we initialize the distance of our source vertex as 0. What we then do is we find the topological order of the graph. And if you remember what the topological order is, the topological order means that for any given vertex V, all the incoming edges, all the vertices U from which an edge goes from U to V, U has to be visited and finished before V. So there were two different methods we found the topological order, and you can think back of an example with a class and prerequisites and what that gives you is the topological order. For this algorithm, we would use the DFS method of finding the topological order. And once we have the topological order, we process every vertex in that topological order one by one. And what we do for each vertex, for every vertex in the topological order, we process that vertex and we relax all outgoing edges from that vertex. What relax means that we calculate the distance of that vertex plus the weight of every outgoing edge, and if it's lesser than the weight, if it's lesser then the weight of the vertex it's going to, we update the distance for that outgoing vertex. So that's basically, and at the end of the algorithm, you would find the single source shortest path for every vertex. If you want to just work for it for one destination, or for one particular destination, you would put in a condition that says, oh, I found my destination, let me return out of this. So you can take a screenshot of this idea of the main single source shortest path. And now I'm going to share with you an image that will contain an example graph, and we will go about, with this idea and try to see how it works. So here, I have this graph here, and we can see that this graph has image A is the graph. It has vertices T, R, X, Y, W, S. So, and like we said, we initialize every vertex except the source. And in this case, we're going to take the source as vertex X right here. So we're going to make this the source. And for this, we initialize the distance to 0. And we create a topological order using DFS. So once we create the topological order, this is what the topological order looks like. We have S, we have R, S, T, X, Y, Z, and there could be multiple topological orders, but this is the one that our algorithm gave us, and so we're going to consider this one. So you can see that S has been initialized to 0, and the distance for every other vertex has been initialized to infinity. We've also put this in a linear. We've made it convenient, and we've placed them in this order. It is not necessary to make it look this way, but we can see that this is the right topological order because of this. Every arrow is pointing to its right. So, and we can also see in this that R is unreachable from S. So R at every point is going to remain infinite because R is unreachable. So now once we have this topological order, we're going to start off by processing the vertexes in the topological order. We're going to first look at S and update the distance for all outgoing edges from S. So we can see from here that S goes to X, so with a distance of 6, and you can see it in this D. So you can see that X has been updated to 6, and S also has an outgoing edge to T with a weight of 2. So we can see that the outgoing edge to T has been updated to 2. So T has been updated to 2, and X has been updated to 6. Y and Z are still at infinite. R is still at infinite. So we finished processing S because it has no more outgoing edges. We then move on to the next vertex in the topological order. In this case, it is T. So we look at T here, and T has outgoing edges, as we can see here, to X and to Y. So let's look at X first. X is 7. So the minimum distance at T that we had now was 2 because we got that from S. So if we go to X, 2 plus 7 would be 9. And that seems to be greater than 6. So we would leave that untouched, and we would still leave X at 6 because that's better. And then the next vertex that T goes to is Y. So we can see that Y is, the distance to Y is 4. So 2 plus, where is it's going out here. So 2 plus 2 equal, Okay, so looks like T to Y, right? So T to Y is, I can see, I'm sorry, here, T to Y, I was looking at Z. I'm sorry, T to Y is 2 plus 4, that's 6. Thank you. So we go from 2 plus 4 to 6, and we get y as 6. So that has been updated here as well. At this point, we have finished processing t because it has no more outgoing edges. The next vertex in the topological order is x. And we know that the minimum distance for x currently is 6. Every outgoing edge from x is y and z. So let's look at y first. So we have 6 as x's current distance. So 6 plus 5 would be 11, but 11 is greater than 6. So we're going to leave that to be, we're going to leave y as 6 because 11 is greater than 6. And the other edge is to z. To z, it's 1. So 6 plus 1 is going to be 7. Am I missing something? Huh. So t we'll be looking at x right now. We have x that goes out to y as 5. X's current distance was 6. 6 plus 5 is going to be 11, which is greater than 6. So we don't look at that right now. And we then look at the other outgoing edge from x, which is to z, and the distance here says 1. So we look at 1. 6 plus 1 is 7. And this should be 7 in this image. So I think there seems to be an error in this image, but this should be 7. Okay, and so let's move on. We'll figure out what happens there. So x 1 plus 6 plus 1 should be 7, and z should be updated to 7. I do not understand how it was updated to. Oh, no. Okay, yeah. Oh, I see what's going on. In this particular graph, for some reason, we're missing an edge from t to z. The edge 2, which is being shown here. So when we were at t, we had the 2 plus 2 that updated the z to 4. But then, so that's why it got initialized to 4, because we are missing that edge right there. It's shown here, as you can see, t2 goes up to z, but here we actually do not see any edge going from t to z directly. So we're missing that edge there, and that's what's the issue. But so when we come to x and we say 6 plus 1, 7, 7 is greater than 4, so that remains untouched. So we still have this as 4. Let's move on. So the next vertex in the topological order in this situation is y, and the current distance at y is, we're looking at here. So the current distance at y is 5. And so now we're going to look at all the outgoing edges from y. So the first outgoing edge from y is -2 to z, as we can see here. So z initially at 4, and 5 minus 2 would be 3. So z gets updated to 3. And the other that's the only outgoing edge from y. So we're basically done with y at that point, and we have z as 3. Finally, we come down to z, which is the last vertex in the topological order. And we see that z has no outgoing edges itself, and we're done with the algorithm at this point. So now we see that from S, we have the shortest distances to every other vertex. And while we were going through this whole algorithm, let's say we reached our destination was X, for example. When we reach the topological order, when we reach X, we know we finished processing X at that point. And X at that point should have had the shortest path from S, and we can just return the distance at that point and finish our algorithm. So that's how you get the variation for finding the distance to one particular destination. But if you just go through the whole topological order, you would find the shortest distance to every single vertex. So with that, with having said that, that's the high level idea. And this algorithm runs in linear time because we are going through each vertex in the topological order once, and we're going through every edge just once. So that's why the algorithm takes O of V plus P, which is linear, because we go through every edge once and every vertex we go through it once. So we can see that it is faster than Bellman-Ford, which is VE. It is faster than Dijkstra's shortest path, which is E plus V log V. So this is a better algorithm, and it can handle negative weights too. One thing that this cannot do well is handle cycles, and I said that I would get back to the cycle portion sometime later. So here, let's create our own little example for a cycle. So in this particular graph, okay, so let's see. So one thing, if there was a cycle at any point of the graph that is not reachable from S. So like here we only have one element R that is not reachable from S, but let's say we had another element P, and P and R had a cycle between them, it would not matter because we're not even concerned with that. Those two vertices, it's not reachable from the source, it does not matter, and we would still, the algorithm works just fine. We'd get our single source shortest path absolutely fine. Now let's say we have a cycle in the part of the graph that is reachable from S. So let's say that t goes to X with 7, and then X comes back to T as well with 5, right? So at this point, let's see, we finished T as 2, and then we went on to X as 6. And when we are doing X, we're updating all outgoing edges from S. So we'd look back, and let's say the weight of the edge from X to T was 5, right? So it would be 6 plus 5, 11, which is greater than 2. So at this point, we're trying to relax an edge coming back to a vertex that has already been finished, but it does not matter because the vertex that has already been finished has a smaller, shortest distance. So the algorithm would work fine. But let's say that the edge from X to T weighed -5, not +5. So if it weighed -5, you would have 6 minus 5, giving you 1, which is less than 2. So now at this point, I'm thinking, okay, I have 1, which is less than 2. So let me update T again. Let me relax the outgoing edges from T again, because T does not have, so everything outgoing from T would not have the correct shortest path. And the algorithm fails. That's just not how it works. The algorithm would fail at that point, and that's the limitation. So you could at that point detect that, oh, I'm going back to a vertex that has already been finished and it's smaller, and I'm getting a smaller shortest distance. And you could fail and return saying, oh, I've detected a negative cycle in this, so I'm going to fail. So that's what's called a negative cycle. So I would just, return back and say that, okay, the algorithm fails at this point. There's nothing more I can do about it here. So that's one limitation of it. The Bellman-Ford algorithm, it kind of overcomes that as well, but it takes longer to run. So really, like Shivanku mentioned, when you're trying to figure out what algorithm to use to find the single source shortest path, you need to make your considerations and trade-offs. You need to see if there is negative edges, if there's cycles, and all those little considerations, and figure out your algorithm. So those were the two main algorithms that we wanted to discuss in this session, and they seem to have, and that's complete. So if there's a graph with a negative cycle, when you convert it to a strongly connected component graph, can this algorithm work on that? So Shivanku, do you have any idea on if the graph has a negative cycle, but you convert it to a strongly connected component graph, and you try to run the algorithm, do you think it will work?
Yeah, so in order to understand the question, the first thing that you need to understand is what a connected component is. So the name connected component can be really misleading because, ironical to the name, whenever we have a graph and we have a we have a graph which in which we have a node A, node B, node C, they're connected, and we have another chain of node C and D which are not connected to node A, B, and C in any way, but they are a part of that graph. So such a graph is called as connected component. So the whole thing on the whole is called as a connected component, whereas they are not even connected. So the name can be a little misleading, whereas these things are connected components. So we look at the graph on the whole in terms of those A, B, C, and D, E graphs being connected as being strongly connected components. So according to question, the question is that is there a graph with a negative cycle? When you convert it to a can this algorithm work on that? Okay, so this definitely can work on that, and the reason for that is, as Raj told you, that whenever we have a cycle, we break out of the cycle, right? So it doesn't matter if it's a negative cycle or a positive cycle, and even if a strong, even in a strong connected component, we follow the same rule. So whenever we have a cycle, we break out of the cycle, and hence both Dijkastra as well as shortest path first would work in such a scenario. So the good thing is that you need to realize that uh, whenever we have a cycle, we need to do is what we need to do is we need to make sure that our algorithm is such that we break out of this cycle, because as I explained you earlier, if we keep on taking a path that is leading us to a cycle, our cost would be something different, because if I have a negative edge which is like costing me -2, and if I go on traversing that edge, then probably my cost for the whole cycle would be something like -infinity, right? Because I'm stuck in that cycle. So whenever you have a cycle, doesn't matter if it's a negative cycle, you need to break out of the cycle. That's the basic funda. So it doesn't matter if you are dealing with a strongly connected component or you are dealing with a graph which is a normal graph. So for both, my advice would be that you just write your code in such a way that whenever you see a cycle, you break out of the loop. In the next session, we'll probably be taking disjoint sets, or something that professor is probably discussing in the lectures and you guys are finding difficult, because as much as I know, professor will be covering dynamic programming and disjoint sets and something else. But we'll see it in about 2 weeks. What's the status and what are the topics that he's going over, and which are the topics that are that are that are difficult. So we'll make our session accordingly, in accordance with that, according to that. And yeah, we'll see you guys on next Friday. That would be what date would that be, Raj? I think that would be 9th. So 9th of November would be the next session at 3:30, from 3:30 to 4:30, and probably we'll be taking up some problems in dynamic programming, because it's a really challenging topic, really interesting topic, and there are multiple problems around dynamic programming which are always asked in technical interviews. So it's very important not just to learn it for CS146, but also to do good in the industry. So yeah, that's something I'm really looking forward to. And that was it for graphs. I really hope you guys uh, can understand which algorithm is used in which situation, and you are able to differentiate how each algorithm works. And good luck for the assignment which is on graphs. Thank you so much. Any last messages, Raj? Anything you want to add on?
So at this point, you can leave the meeting if and yeah, the next meeting is going to be 2 weeks from today. Thank you for joining us for this session.